So we're now ready to talk about the structure of the atom, the particle that makes up all of the matter that we're going to talk about in this course. This is the topic of Chapter 2, or one of the topics of Chapter 2 in your text. At this point, I'm hoping you have already viewed the History of Atomic Structure crash course video that's also on the topics page for Chapter 2. Here you're going to find the quick version of the development of the atomic model. It's important for you to have heard some of the story of how the view of the atom changed from ancient times with Democritus into more modern times with Dalton, Thomson, Rutherford, Bohr. Okay, and viewing this up to about the 6-minute 30-second mark will give you the background you need for this chapter. We will go deeper at some point in the future. So if you ask yourself the question, what is an atom? We can take this from a simple level to an extremely complicated level. And frankly, in this course, we're going to keep it fairly simple. I think that you can consider an atom as the smallest piece of matter that we know of. Now, yes, you are a bright bunch of kids. You know there are things smaller than the atom, okay? You've probably heard of quarks and gluons and all kinds of things. We're not going to dig deeper than the atom. That's our smallest particle. I guess you can consider the protons, neutrons, and electrons, but we're not going to go any farther than those. So an atom is the smallest piece, as Hank said in the video, of something, the smallest piece of cheese, the smallest piece of iron, okay? It's just a little nugget of matter. There are 3 subatomic particles that we will consider in this course. In your text on page 80, you will find a detailed breakdown of the characteristics of these. It would probably be wise to pause the video right now, open your book to page 80, and just take a peek at that table near the top of the page. We will be focusing on these 3 subatomic particles in this course, the proton, the neutron, and the electron. What do we need to know about these? Oops. The proton is located in the nucleus of the atom. Okay? It is also a particle that has a charge of +1 and a relative mass of 1 AMU. AMU stands for atomic mass unit. If you look on page 80, you're going to see a mass in grams that is an ugly little number and nothing you need to memorize. It's always something you can look up. Electrons are particles that are located in levels surrounding the nucleus or outside of the nucleus. They have a charge of -1, and their mass is roughly 1/2000th of an AMU. So quite a bit smaller than that of the proton. Lastly, the neutrons are particles that are located also in the nucleus. They have a charge of 0, and their mass is also approximately 1 AMU. Okay? So nearly the same mass as that of a proton. Actually, a tiny bit more mass than the proton, but not enough to worry about. And so we can simply call them 1 AMU each. I'm suspecting that you are already somewhat experienced in writing the symbols for the elements, but that may not need be the case, and if not, we'll go over it and we'll teach you how to do this, okay? Generally, when we write the symbols, we write them in the manner that you see here, okay? Where X stands for the symbol of whatever the element is, and on the periodic table, every element has its own symbol. Z represents the atomic number of that element, which represents the number of protons in the nucleus. That's a U. And A represents the mass number of the atom. And the mass number is the sum of the protons and the neutrons. So here we have a few examples of writing symbols for atoms based on the given information. So what I would like you to do is to pause the video and write the symbols for these three atoms, the copper atom, the potassium atom, and the boron atom, and then start back up again after you've done so and check your work. So the first example would be Cu for the symbol. The atomic number is 29, and 63 is the mass number. Just a note here, these are all atoms. So in the case of atoms, we assume that the number of protons is equal to the number of electrons in the atom. And at the moment, on these symbols, as written this way, we are not indicating anything specific about the number of electrons other than the fact that for an atom to have a charge of 0, the positives must equal the negatives. And so we can make this assumption that the electrons and protons are the same. Potassium symbol would be written as such. Boron symbol as you see here. If you turn to page 84 in your textbook, you're going to see a table that gives some data about various atoms, the nuclear compositions for some of the smaller atoms on the periodic table. And I'd like you to open to that page now and pause the video for a moment to examine the data and start by answering this first question here. This is number 1. Right here. What do you notice about the number of protons in each of the atoms for carbon or neon? I'm hoping that you notice that for each isotope of carbon, and there were 3 different flavors of carbon or varieties of carbon or isotopes of carbon, that the number of protons was the same in each one. And it is the number of protons that identifies an element's name and characteristics. So any atom with 6 protons in its nucleus is going to be identified as carbon. Same would be true for neon. Every one of the neon atoms on that table on page 84 has 10 protons. However, if you look at carbon on a periodic table, you will find a mass for carbon on the periodic table that is 12.0107 or thereabouts, depending on which periodic table you're using. And that does not match any of the masses given for the 3 possible varieties of carbon on the table on page 84. But if you take a look at the abundances in the final column, you will see that most, by far, of the atoms of carbon have a mass of approximately 12.0 AMUs. There are about 1% of carbons that we know of in the universe that have a mass of about 13, and very few that have a mass of 14. So, the mass number found on the periodic table is an average mass taking into account the isotopic abundances. Carbon-12 counts the most in the averaging, and thus the mass is closest to the mass of carbon-12, that isotope. A little higher to account for the few atoms that would have a mass of 13 or 14. Last page for this video is writing chemical formulas. There are molecular formulas with which I think you are probably fairly familiar from your biology class. I know you've heard of C6H12O6, H2O, maybe not CH4. Okay, those are molecular formulas, and what those do is they show the number of each atom in one molecule of this substance. Structural formulas indicate the way that the atoms are arranged or connected to one another. I bet that in your biology class you saw a water molecule that might have looked something like this, okay, where the red atom represents the oxygen and the hydrogen atoms are represented as the little white atoms connected to the red oxygen. That's more of a structural formula, okay? And we will talk at great length later in the course about molecular structures. So pause the video now and take a few moments to look up and write down the molecular formulas for these 7 compounds that are listed at the bottom of the slide.